Actually, maybe can we start with how does, if we want to understand how to do mathematical modeling, how does cubism and chickens help us get that conversation going?
Yeah. Okay. Yeah. Well, you're referring to in my 2017 paper, models are stupid and we need more of them. I have this part in it that's called the parable of the Cubist chicken, and it's not so much a this is how you do modeling point. The point is about precision and therefore, kind of making the point that models are useful because words are imprecise. So this was a true story. A very silly story that happened when I was in college. So I was probably about, 19 or 20. And a friend and I were messing around and we were like, let's just say definitely not sober. And we went to collect a third friend of ours who was in a play. And we had already seen the play, so we didn't need to go watch his play again. We were just waiting for his play to end so we could take him and go off on an adventure. Which would probably
continue not being sober.
Yes, and continue to be even less sober. And this was at Wesleyan University in Connecticut, and in the old 92 theater, there's a basement with couches and toys and shenanigans and all kinds of theater-y things. And there was a big bucket of Legos. And just kind of absentmindedly while we were talking, waiting for our friend, I was playing around with Legos, just putting Legos randomly together as like a thing.
So is that a normal thing to have Legos in a theater waiting room?
I mean, I have no idea, honestly. I hope so.
Okay. I've never been to the US, so I don't know. Maybe in Europe, it's not really the norm.
No, I don't think it's necessarily. I think it's more just like knickknacks and sort of things to play with or improvise with. So maybe Legos are useful in that regard. I haven't spent that much time in theaters, so at least backstage. But I learned very quickly that I'm a very bad actor.
You've tried?
I tried. I tried in my youth. I'm not good at it. I don't know what it is. Too self-conscious, maybe. But we were futzing around with the Legos, and I honestly can't remember. And I've asked my friend, who's now a film editor in LA, if I said, do you remember? He remembers the story. I said, do you remember which one of us first pointed out that it looked like a Cubist chicken? And he said, no, I don't remember. So one of us looked at this kind of smash of blocks and just kind of were like, if you squint at it, we're like, look, it's like a Cubist chicken. And the other one of us said, oh, you're right. It's totally a Cubist chicken. Like, look at the Cubist chicken. And being not that sober, we were, I think, more pleased with ourselves than we had any right to be in this case. We and it would have ended there and just it been forgotten to the time. Like, oh yeah, there was this time where for a couple minutes we talked about how one of us had made a Cubist chicken out of Legos. Except that shortly after, our friend that we'd been waiting for came down and said, hey guys, what's up? And one of us held up the mash of blocks and said, look, it's a Cubist chicken. And he was totally sober, having just been in a play, and just gave us this kind of like raised eyebrow, like, how is that a Cubist chicken?
Yeah.
And I just said, well, look, here's the head and there's the body and here are the feet. And my friend, who for the last 10 minutes had been agreeing with me that it was in fact a Cubist chicken, just got very upset and said, no, the whole thing is just the head. And there's the beak and these are the eyes and this is the crest. Because it was a rooster in his mind. And we realized that we had been using the same words and calling it a Cubist chicken and agreeing for 10 minutes that it was in fact a Cubist chicken. And as soon as our third friend had asked us to explain exactly how it was a Cubist chicken, the whole thing fell apart and we realized we were talking about completely different things. And the reason this story stuck with me is because I think of it as an analogy for something that happens all the time, is that we use words in ways that feel familiar, that allow us to feel like we agree with each other. Because a lot of words are vague, like cubism is vague. Chicken is pretty clear, but like how something can be a Cubist chicken, if I just told you, imagine a Cubist chicken, everybody listening to this is imagining something slightly different. But as soon as you say, explain to me exactly how the Cubist chicken is made and what the parts are, all of a sudden we have to be very precise. And I thought about this a lot after I got more into, becoming a scientist and spending time in psychology and social science departments, and realizing that a lot of the times the words we use are very vague. And we use words like identity or emotion, anger, fear, behavior, right? All kinds of sort of psychological or social constructs, the economy, right? They're vague words and there's ambiguity. And it allows us to talk to each other using the same words and think that we're talking about the same thing. Whereas in fact, in our own minds, we're thinking about completely different things. And this leads to problems when we try to do science, right? I think there's ambiguity in language for very, many reasons, some of which are adaptive, but...
Wait, what might some of the adaptive reasons be?
Well, I think it's very efficient for one, on the one hand, if I can just sort of give you an impression of the sort of category of things that you need to deal with without having to specify exactly what I'm talking about. Also, it allows sort of differentiated groups of people to coalesce around a common cause because they can all view the cause slightly differently but use the same word for it and therefore internalize the meaning. And I think it's actually really useful in coalition building. It's also useful, for, let's say, slimy politicians to make vague promises and say, we're going to use, let's say, I don't really need to go into any specific examples, but, I'm going to do this and use ambiguous language and sort of refuse to answer when they're asked, what exactly do you mean? So it allows lots of different, let's say, voters to say, oh, they're going to do something that I like because I'm going to interpret their language to mean this, whereas someone else can also say that they're going to do what I like because I'm going to interpret their language this way. And both of them are right because there's ambiguity in the language, but also both of them are wrong because neither of them have nailed exactly what is going to happen because there is no precision in the promise. So there's some really great literature on this, at least starting in the 1980s from communication. There's this really wonderful paper by Eisenberg, I think, called something like Ambiguity as a Strategic Communication Strategy. It's I'm sure it doesn't use strategic and strategy. I'm sure it's a better title, but but when we're doing science, right, we want to say this is what the world is like, and we're going to form hypotheses and theories that are based on particular deconstructions of the world, and say, well, if this is the case, then this will happen. And if this other thing is the case, then this will happen. And that's kind of what a lot of science, that's at least the goal of a lot of science. And to do that, we have to say, some of the goal of science is just description. Say, this is what this is, and this is what this is made of. But in either case, right, we need to be very precise about what those things are, what we are talking about, and not allow ourselves to be bogged by imprecision. But imprecision is rampant in, say, a lot of psychology and the social sciences, and probably other fields as well. But
I feel like one assumption I've always had, or intuition, is that in psychology it's much worse because we talk about we study concepts that we also use as humans in everyday speech. I feel like in physics, maybe if you're talking about neutrinos or whatever, it has a much more precisely defined meaning than if you talk about emotions or whatever that you might use every day in all sorts of contexts.
Oh, absolutely. And then there's a couple of reasons for that. One is exactly what you're talking about, that everyone sort of feels like they have a claim to already some level of expertise, which to some degree we do, right? Because we are humans and we know what it's like to be a human and be around other humans and live in society. But you're right, both psychology, I would say the social sciences too. I mean, if you're, a sociologist or an anthropologist or an economist, you're using words like, culture or, I mean, just we could stop there, right? There's nobody ask 100 people what culture means, you get 150 answers. And, psychologists, absolutely, because we're dealing with mental states, right? What it feels like to be something and what it appears like and what it seems like. And it's not always clear that the way we sort of cognitively parse the world is, in fact, the best way to describe it precisely. Another issue, right, is that, there's this mismatch between measurement and theory in a lot of the sciences, basically all the social sciences and almost all of psychology, except for maybe, some of the more clear-cut cases of like neurophysiology or behavioral science or psychophysics, where there's a mismatch, right? Or sorry, not a mismatch, but an imprecision to the mapping between the theory and the measurement. So this is what some philosophers call the difference between the exact and the inexact sciences. And it's probably not quite such a dichotomy, but more of a continuum. But, if we're doing physics, let's say a lot of physics, the theory is about the thing that is directly measurable. It's about that, right? So the theory is about how force and mass and acceleration are interlinked. The theory is about how charge and fields affect one another, right? The theory is about how temperature and pressure are interlinked, right? That's what the theory is about, and those are the things that we are measuring. And notice that, any physics equation, all the components, all the little letters, there's a unit of measurement associated with them all. And that is not the case in psychology or the social sciences or even a lot of biology, right? We're dealing with much more abstract concepts. There's an inexactness to the mapping between what we want to talk about, like fear or consciousness. Well, not consciousness is its own can of worms, but let's say, memory, right? Or, I don't know, even behaviors, certainly things like culture, cooperation, disgust, whatever. We have folk concepts, right? We have an idea in our head of what kind of that means to each of us as an individual. But then you say, well, how do you measure fear? How do you measure generosity? How do you measure willpower or patience, right? Well, you say, well, but I don't know. It's like this whole gestalt of different kinds of amalgams of behaviors and perceptions. So I'm going to operationalize it in, let's say, an experimental context or some, some data collection where, I have this, data that's been collected from some survey, and it allows me to sort of kind of get at the kind of thing that I'm kind of talking about. And it just makes it much harder to do this kind of science in general. And this isn't actually about models per se. This is like a sort of just a general limitation to trying to do science on complex emergent phenomena that involves, a lot of organization. So I was really influenced by the philosopher Bill Wimsatt, who was my I sort of hate this terminology, but my academic grandfather, right? He's my advisor's advisor. He has this really wonderful paper from the 70s called Complexity in Organization. And he kind of talks about, basically the difficulties in trying to do theory on anything complex. And he was really talking, he wasn't at that time really interested in psychology per se or behavior. He was, interested in things like evolutionary biology and developmental biology. But even then he was saying, compare a rock and a fly. The parts of the rock are basically pretty straightforward. And the way it's organized it's kind of uniform. There's a crystalline structure maybe, and maybe there's, different elements that work together. But But organizationally, it's pretty easy to pin down, whereas a fly has all these different systems that are, and you can describe it at many different levels, right? At the cellular level, the hormone level, at the organ, like the level of the organs, the level of the body parts, what their function is, what their behavior is, how they interact. And there's both up, sort of bottom up and top down interactions, so that what the fly sees, let's say in the world, interacts its physiology, and then the physiology affects how it sees things. And all these things make it very, very difficult to make sort of concrete theory. It doesn't mean it's we shouldn't try. It just, I think, just sort of like being aware of and paying attention to these kinds of complexities should make us a bit more careful as scientists.
Yeah, I mean, one thing I was wondering also when reading one of your, I can't remember which one it was, papers, is that at some point I wondered, like, how did we get here in terms of psychology? Like, why is this so bad? Is it just because that it's so difficult that people say, well, we're just not going to do that then? Or, I mean, there's of course many reasons why. But yeah, do you think it's just like at the complexity seemed so high that people said, okay, let's just try a different approach almost?
I think there's many reasons why, as you say. I think so two things immediately come to mind. One is that one just comes back to exactly what you were talking about before, which is that because we are humans, we sort of feel like we have a claim to understanding human behavior without needing to. So, like, if someone says I'm a physicist and someone says, well, I don't, it's going to be difficult for me to explain what I do. Most people feel very comfortable being like, yeah, I admit it, that I accept that. You're a physicist. Physics is very complicated. I don't have that kind of expertise. So I'm going to sort of, defer to you, or understand that it would take a very long time and be very difficult to understand things at the level that you do. If you say I'm a psychologist and I understand how memory works, people say, well, I have memory. Tell me how it works. I should be able to understand that right away. And I think that sets up two sides to this system where, first of all, people sort of come into things without the expectation that it's going to be as hard as it needs to be. So people say, well, I should be able to, as a first-year graduate student, be doing cutting-edge research and be coming up with really amazing research questions and getting published in top journals because I already, have the ability to form good questions about memory or learning or behavior because I'm a person. Whereas, like, I'm still in that phase. Yeah, right. And this is it. It's culturally indoctrinated in the pedagogy of psychology and other fields. Right. It's very common for students to think that, and for professors to encourage them to think that way. By the end of your first year, you should be submitting papers to top research journals. Whereas if you go into biochemistry or high energy physics or cosmology or whatever, nobody would think that. Nobody thinks that in your first year, you should be doing and producing leading research. Maybe you'll be on a project that's cutting edge, but nobody thinks you should be leading a project that is cutting edge in your first year because it would be crazy. You have so much to learn.
Somehow, actually, I thought it was almost the other way around because I guess I don't know much about physics, and I don't read much about popular physics, but one of the few things I know is that the quantum revolution was done by people in their 20s or something. Wasn't all of that? A lot of the breakthroughs in the early 20th century came from people who were younger than 30, right?
That is true. A couple things.
Somehow, my assumption was that.
I think there's a couple things about that. One is that it is sort of the outlier case. The other is that, at that point, people in their late 20s will have been doing this, sort of consistently for a while. And the other is that we're talking about theory, right, and math.
Yeah.
And they're coming in and basically looking at how mathematical functions work. And a lot of really cutting edge work in mathematics is done by young people. And there's a lot of sort of speculation about why that is. It may just be that that's the age in which you can completely focus on some sort of crazy abstract thing. and not worry about anything else in the world. But yeah, no, that's a fair point. So I think that the other side of that same issue with something like psychology is that people who are not scientists are interested in knowing about human behavior in ways that they are less interested in learning about physics or biochemistry or the behavior of insects or fruit flies or something. And so you can write like how many popular psych books are there on the bookshelves now? How many came out this year, right? Like an absurd amount, right? And because there's money to be made in telling people things that are either both counterintuitive or totally intuitive and supports what they thought all along and helps them bolster their argument. And so people love these kinds of books. And so there's money to be made. And this also helps elevate people who, let's say, aren't necessarily doing the most rigorous work, because by being kind of vague and ambiguous and imprecise, but, they can become salespeople. And they can become very successful in this way. And because academic success and popular success, while there's not a one-to-one mapping, they're linked, right? If universities love to hire people who have bestsellers. So the other thing is historical. I mean, the only thing about, like, you sort of related to that point, like thinking about someone like Sigmund Freud. And I have a soft spot for Freud because my dad, it was a psychoanalyst, and
oh, really? Okay.
He used to teach Freud at the New York Institute for Psychoanalytic Training. So I have a soft spot for Freud a bit, but Freud, it was started as a neurologist, and wanted to talk about consciousness and emotion and all that kind of stuff. And he sort of quickly realized that there was no way to make a path between neuroscience, especially as it was at the end of the 19th century, and consciousness and memory. There was just no way to make that link at that time. So he just said, well, forget it. I'll become much less precise, and I'll start using metaphor and obviously become extremely successful and influential in this way. There's other things, right, which is, and related to all that, like a lot of the early psychologists were extremely rigorous and scientific. I mean, they were all crazy, because all early scientists in any field are crazy, because you have to be crazy to start a totally new field of science, especially at a time where science was much less institutionalized as it is now.
By early psychologists, what are you talking about?
Well, I mean, I'm thinking of, a few people come to mind, but like Wilhelm Wundt comes to mind. Mm-hmm. I mean, so that guy's
psychophysics.
The early psychophysics. But like, if you read about Wundt, he's insane, right? He was, he got hired as a philosophy professor at Leipzig, and he kept asking for a lab, and they finally, after years of asking, gave him like a closet, and he purchased all his own equipment and was just doing this all in his spare time. And I found there was some retrospective I found that published his teaching schedule for his first 5 years at Leipzig, and he taught cosmology and philosophy and anthropology and psychology, right? It's like it's insane. And he was just like, he was part of his research was psychophysics. Part of it was just asking people, like, what'd you see? What did it feel like? Right? And like voluntarism. But he was writing things down and trying to be very precise, because he had to convince other people that this mattered.
I mean, was he trained as a doctor physicist?
That's a good question, and I don't know.
Okay, because I feel like those are probably the two, and philosophy, right? Or probably the three reasons from which people came to psychology.
I think probably philosophy, but I'm not totally sure. Possibly medicine. I don't know. You're right. There was a lot of mismatch, or not mismatch. I was going to say mishmash, which is apparently a word I use often.
Okay. It's a good German word.
But then, sort of American behaviorism like Watson and Skinner, and especially Edward Tolman, like those early like behavioral things, like all the cognitive map stuff, it's incredibly precise what they're doing. And a lot of the behaviorists were the first people. They were extremely rigorous, and some of the first mathematical models in psychology came out of behaviorism, right? Like Rescorla and Wagner in the 1970s is great, and that leads you directly from Rescorla and Wagner in psychology to people like Sutton and Bartow in computer science, who formalized it into reinforcement learning, which is now a key component of machine learning. People who learned that then became neuroscientists like Wolfram Schultz, and then discovered, the prediction error system in the dopamine system. And it's like, I think of there as being like a direct line from one to another. And, it's really sort of, I think sort of the power of formalism and precision is that you can take this thing, like, here's how it works. Oh, well, if it works that way, then we can program that algorithm into something else. Well, if we're familiar with that algorithm and we know it works, then maybe the brain is actually doing it. No, look, we found it in the brain. So, yeah, but I don't know. That was a very long-winded answer to your question. So maybe we can move on.
Yeah, exactly. I've always forgotten. Oh yeah, how we got there, psychology. Yeah. So maybe one thing I found interesting in reading I think this is in Models Are Stupid and We Need More of Them, the paper that I found interesting that I somehow never thought about in that way is that you said like that the point of a formal model is to just specify the relationship between variables. And like, I don't know why, but somehow when I read that, I thought like, well, yeah, of course. But then I realized like somehow in the way I've been thinking, as like someone who studied psychology, somehow, I don't know, in that precise way, I never thought about it, which is really seems like a bizarre omission in my thinking.
I think it's very common. I mean, I think that, we come into things, and especially like with something like psychology, but we sort of have this idea that we know how the world is made of. We know what the world is made of and how it's made and how it works. And all we have to do is figure out, what exactly the things that we know about are, like how exactly they're constructed, and then how they affect each other. But I think a huge part of science is figuring out exactly what's in the world to begin with, and how those things relate to each other. And I think I was extremely influenced when I was a grad student. I read this paper from the early 1970s by Stuart Kauffman. And so Stuart Kauffman, I don't know if you're familiar with his work. He's
don't think so.
Kind of legendary in complexity science and complex systems. He was kind of an early person at the Santa Fe Institute and did really all this extremely influential work on rugged fitness landscapes and epistemic gene networks. So, thinking about like the emergence of structure and evolution. But he has this, he started as a medical doctor and then sort of switched to sort of this, computational complexity science. And on the way there, or very early in his career, he published this paper in the conference proceedings that eventually became the Journal of Philosophy of Science. And it had some terrible title that I can never, it's called, I think, On the Articulation of Parts in Biology and the Rational Search for Them.
Good title.
It's a terrible title, but it's I think of it as like to me, it's like the most important philosophy paper in my arsenal.
Oh, really? Okay.
What
cited in here? Okay.
I cited in almost everything sort of.
Oh yeah, articulation of parts, explanation in biology. It's even worse than you said. I'm just going to highlight that then. Okay.
Yeah. So I mean, what Kauffman points, the paper is really about hypotheses, and so I think the point that is that I take from him, and this is sort of Kauffman then filtered through me, is. Most of us are very familiar in our training with the idea of science as hypothesis testing. Like we come up with hypotheses. Like this is sort of the, grade school version of Francis Bacon. Like the scientific method is we come up with a hypothesis and then we test the hypothesis and we, the evidence either supports or doesn't support the hypothesis. Kauffman's point is, well, where do these hypotheses come from? how do you make a good hypothesis? And it would be a very bad idea. And in psychology, it's a very common way to do things, but it would be a very bad idea to just say, I'm just going to make it up, right? Based on nothing, based on my sort of intuitions. Now, obviously, I do believe in expertise, and I think that over time, experts do gain an intuition for things and should be able to trust their intuition to some extent. But the point here is not about, how rigorous or how much of an expert you need to be to make a hypothesis. The point is that what a hypothesis is the articulation of parts. And what that by this he means, and this is also an idea that Herb Simon at the same time was talking a lot about, and also Bill Wimsatt, but sort of there's all these great papers in the late 60s, early 70s on this kind of stuff. But the basic idea is that if you want to form a hypothesis about some system, you need to have a question that drives what you want to know about the system. And in pursuing that question, you have to decompose the system into parts. And what I've added is, and the relationships between those parts. And there's no single correct decomposition. I mean, probably the only single correct decomposition is to say, well, everything is quarks or strings or in brains or whatever, the physicists say we're all made of at the fundamental level. But like beyond that, right, we're talking about emergence, and we're talking about things in the world that are made up of other things. And so any particular theory abstracts away a lot of levels of organization and says, well, I'm going to focus on the neurons, or I'm going to focus on perception. I'm going to focus on memories. I'm going to focus on physiology. I'm going to focus on behavior, and these behaviors and not these other behaviors, or these organs and not these other organs, or these aspects of perception or context or whatever it is, and not other things. I'm going to decompose the system into the parts that I think are most relevant to my question, and think about how those parts, what are those parts made of? What are the properties of those parts? How do they affect each other and relate to each other? And then that allows me to construct a hypothesis. The hypothesis, any hypothesis, is about the parts, is a story about what the parts are, what they're made of, and how they relate to each other. And what they do or don't do. And so for any particular system, there are usually multiple ways to decompose it into different sets of parts and relationships. And exactly what is sort of the right decomposition depends on the question. And it's sort of a great decomposition is one that really shines light on the question and allows us to get more information out of it that allows us to make better predictions, let's say, or have deeper understanding. And, I think often sort of what I think Kuhn would call paradigm shifts is the introduction of a new decomposition, a new articulation of a system into parts that allows new kinds of questions or better questions to be asked about it. Okay? When we went from Newtonian mechanics to quantum mechanics, right? We're decomposing the world into different kinds of parts, and we can ask new kinds of questions about it. Now, the reason Newtonian physics is still useful is because that decomposition still allows us to answer questions in a useful way. And depending on the questions we ask, right, decomposing the world differently gets us different places. So here's what I think was so cool about the Kaufman paper, in addition to all about that, is at the end, he says, well, and once we can do this, once we can decompose our system into parts, and we've articulated what the parts are, what their properties are, and how they work, and we're precise then about our hypotheses, we can encode our hypothesis in what he calls the cybernetic model. He uses cybernetics because that was the big thing back then. But what he's basically talking about is a computational model. And this is like 1970, he's writing this. before the personal computers at that time weren't even invented.
Yeah. Yeah. The one part that I found really useful just for me personally relates to part of what you just said, and also basically the title of the models are stupid, namely the part that you have to, choose, you can decompose it in all these different kinds of ways, but you have to choose the specific ones that are most relevant for the question you want to ask. And again, this is very obvious once you state it like that. But like, I think one thing, especially I do some social interactions and cooperation, that kind of stuff in my main work. And I often find myself just adding stuff, thinking like, well, this also has an effect, and this has an effect, and that has an effect. And then I found it just really, how should we say, it's almost freeing to know, like, yeah, you don't have to deal with everything. Like, just focus on the things that explain the thing you're trying to understand.
Yeah. I think the frustrating thing about doing this kind of work on, especially with social behavior, is that it does all have an effect, right? It does all matter to some extent. But, when we try to build theories, what we want to kind of do is say, well, what is the thing that matters the most? What are the things that matter the most? What is the sort of things that, fundamentally structure the interactions and provide sort of the foundational structure, and you can almost think about this as infrastructure. Like, what are the things that constrain and provide the affordances to the behavior the most? And then you can start adding things. Well, but if this is also the case, then it changes things this way. Or this is a new affordance that people have, then they can do things this way. And, there's, if they come from this culture, then, perhaps then it would be more adaptive to do that. Or, whatever it is, you can start adding things. If they're sick or if they have a mental illness or whatever, you can start adding things and changing things. But what you want to start with is a foundation of what are the key, what is sort of the key aspects of this behavior, this scenario that, what is the situation here demanding of people, and what are I think this is also a call to think about things more instrumentally than a lot of psychologists do.
Which maybe more instrumentally?
What I mean is, and you're probably already doing this to some extent when you're thinking about things like cooperation, but there's a tendency, I think I've seen at least in psychology, which is something that I think separates it and creates an artificial divide between psychology and the other social sciences, to focus on the internal perception of something, the phenomenology of something, and stop there. I'm not saying these things aren't important, but when you're studying things like identity or emotion or whatever, people will study emotion by asking people how they feel, or saying, well, how did you feel when that happened? Or imagine a time when this is how you felt. People will study identity by saying things like, who do you identify with? How do you feel? Like, what is, what identity feels appropriate? And those things that research is potentially useful and can be great, but it needs to be tied to something that, to the kinds of questions that ask, well, what is the function of these, what would it mean for behavior to feel that way? What purpose does an emotion serve? Maybe it's not adaptive, but at least what happens when this emotion is present? The emotion is just, or the phenomenology is just what we call it internally, right? But what behaviors are out in the world, what behaviors it produces, what classes of behaviors it does, those are, I think, the things that really matter. In part because they are the ones that, that actually matter to other people. And to, what we really care about is what people do, not what they feel. We care about everyone cares about how they feel yeah. and what other people do. Right.
Yeah.
But, the other thing is that if we want to know why people feel particular ways, and other ways, right? We have to think about the sort of social forces and the evolutionary forces and the cultural forces that create minds that do things and not other things. And that requires understanding the consequences of those internal psychological states.
So one question I had, which I wrote down, is what exactly is the difference between a formal model and a theory?
Sorry, I paused to take a drink. That's a great question, and it's one that I there's some debate about, and I'm not sure that I'm going to be 100% convinced by my own answer here, but I'll do my best. Right? I mean, the word theory is to some extent fairly imprecise.
Yeah.
And this is the issue, right? A formal model is something that is much more precise. So I'm more comfortable talking about, what a model is than what a theory is. But I think of a theory is an idea about what something is made of and how things work, what things are made of and how they work. So you can have a theory that says, well, my theory is that when this, something is the case, then, something will happen. That would be a theory. More precise theories are better theories usually. Another way to put it that seems oppositional, but I think it's complementary, is more generalizable theories are better theories. Now, generalizable theories aren't necessarily more precise, but it's important. There's this idea from sociology that has not migrated into psychology, and I only recently discovered, but it's the sociology papers on it are from the 1980s. This idea of the importance of scope in what they call scope in describing a theory. And the idea is basically, well, if you say I have a theory about segregation or polarization or whatever, you have to say when your theory applies and when it doesn't apply, right? What are the conditions under which, what conditions need to be met for this theory to be applicable and what doesn't? This was a big critique of, in psychology, of, let's say, the sort of Kahneman and Tversky decision-making biases in heuristics literature that, especially Gert Gigerenzer launched, right? I mean, this was his, I think it's his most compelling critique of that stuff, which was, to say, well, you say you have an availability heuristic or a confirmation bias or whatever. Well, there are cases in which these things are incompatible with each other, or having one heuristic would preclude having the other heuristic. So when do we expect one heuristic to be dominant, and when do we expect another heuristic to be dominant? And there's basically nothing in the Kahneman and Tversky literature that tells you the answer.
Is there like a single paper where Gigerenzer questions that, or? Because I know that he's criticized them, but I've never actually read his critique properly. I
don't know. I've read a lot of his papers, and I can't. And he may have just. I attended a summer institute at his Max Planck in 2012, and he may have just said that out loud, honestly.
Okay.
But I think it's in some. I don't know. He's written so many papers.
Yeah, I'm also asking because I always put the papers I always have references for these podcasts.
Okay, yeah. Just read everything that Gigerenzer wrote. Everything he wrote.
By the way, I was just briefly talking about papers. Another thing I'll put in there is there's a good, I thought a really interesting paper by Matthew Rabin on, it's a commentary or something. It's not like an actual paper about, I can't remember what it's called, but it's, that was also one of those like, someone giving you a bit of a slap while you're reading it, when he said, like, as you said, like a theory has to be broadly applicable. There's no point in having a theory about, like, I don't know, his examples, like about a certain kind of farmer in a certain kind of year. You need a theory that applies to all humans. Kind of all the time. And
it's difficult, right? Because what you want to do is to say, well, I want my theory to be applicable to a particular situation, and a theory that's applicable to a particular situation, especially when we're talking about human behavior, is one that's probably not applicable to any other situation, the more precise you can get it for one situation, the less it's going to apply to anything else. So there's this trade-off, but also, I think the less you know about, or the less formalized a system is, or a type of interaction is, that the more you need sort of broad, generalizable theory. Like if you're going to, so cooperation is a great example of this, right? You need to understand the simple prisoner's dilemma, 2-player game without any institutions or punishment or group structure, and understand how that works before you want to start building, okay, well, now we understand how this works, how cooperation works when there's iterated interactions, or when there's a population structure or kin structure. Oh, now we can add sort of contingent strategies like reciprocity. What happens if we add, a multiplayer game? What happens if we add the ability to punish non-cooperators? And, what happens if we add things like reputation? What happens if we add things like hierarchy or power dynamics? Those things are all important, but you need to understand the baseline theory before you can start making sense of the things that are more complicated.
Yeah, I guess that's true too. I think the thing that really spoke to me when I read this is so I am using the prisoner's dilemma, and in one of his footnotes he wrote something like, and we certainly don't need another addition to the 40,000 explanations of how people behave in the dictator game, something like that. And then I thought I am thinking way too much about the paradigm I'm using rather than the general thing which is supposed to apply to.
Yeah. I have something to say about that, but I also want to go back to your question about theories versus models, which is that, Michael Muthakrishna and Joe Henrich have this nice paper called A Problem in Theory. And they have this delineation, which I find useful, between a theory and a theoretical framework.
Okay.
And I think
that? I've read the paper, but I can't remember that distinction.
Yeah, I think the idea is that a theory can be anything like what I was just talking about, if X is the case, then Y will happen, and if Y is, A is the case, then Y will happen. If B is the case, then Z will happen. But a theoretical framework is kind of a collection of theories. It is a sort of and moreover, it's a sort of guiding set of assumptions and principles to say, well, all of the theories that are built on this framework will have assumptions that look like this. These are the assumptions that will go into all of our theories. These are the kinds of principles and things to guide, the kinds of questions our theories will be about. And I think the theoretical framework could be almost, I sometimes think of it as like a meta theory. It's a set of parts from which to make theories, if you will. And that's a metaphor. And I don't know if Mike would agree with me, but I bet he would agree with most of it and have some bones to pick. So
that's pretty good.
Yeah. So, and a model is a model is a formalization. A model is to say, well, I have a system and I have questions about the system. So I've decomposed the system into parts and relationships between these parts and the properties of these parts. And I'm now going to formalize to say, well, I'm going to set it up all my assumptions and lay them out very clearly. You can do this mathematically as a set of equations that relate certain variables to other variables. You can do this computationally by saying, well, I have an object that has these parts, and these, are the things that it can come in contact with, and these are its affordances and the ways that it can behave and make decisions and affect other parts of the system. And then you just kind of work it out forward and see what are the consequences of making all those assumptions. I use this phrase, which I stole from the Jeremy Gunawardena, who's a systems biologist, which was that a model is a logical engine that turns assumptions into conclusions. And I really always love that line. And, I think that's all it is. And the reason why this is useful is that our brains are very bad at thinking through the consequences of our assumptions, especially about complex systems. And so, and the model allows us to start messing around with the assumptions. Well, what if we assume this different thing? What if we change the situations here? What if we add this new constraint? What if we, make it so that, this thing, whatever, some property is slightly changed? And we can often find things that we wouldn't necessarily intuit, like, critical transitions and phase changes. And we can find nonlinear dynamics where something goes up and then it goes down. So I find them incredibly useful as sort of tools for thinking. I mean, I always like this. Murray Gell-Mann, the physicist, and once said, models are prostheses for the imagination.
Yeah. Yeah, I really like that too, because I think also just for like checking, just seeing like what happens if you change this assumption, like does it really require a very precise parameter? What happens if you just mess around with it a bit? So like, okay, I think many people can agree that formal models seem like a great idea to specify what you're doing. At least in many contexts, it's a good idea to do that and all that kind of stuff. But for me, really, the big question is, like, what do we not do then in terms of education? Like, if you have a, psychology undergraduate or something, like, or graduate project or whatever, like, program, not project, we already have all this stuff. So if we want to add, I guess you're not exactly saying that we should add this as part of the curriculum, but it sounds like it in some places. But then, we have to do something less, basically. So what is...
Yeah.
You see what I mean?
I do see what you mean. And no, this is not the first time I've heard this. I think we do have to change the curriculum. Absolutely. I mean, certainly psychology is a mess, and the way it's taught is just not, I think, it's the sign of a very young field that is maybe, I'm very sympathetic to a lot of Paul Rosin's arguments that he's made in sort of psychology, got into hypothesis testing too quickly and should, do some more exploration. But I also think that, toolkits are really important. So, I think of this really differently because I did my undergraduate in physics, and I then went to a graduate program in psychology later. And I was, as in most graduate programs in America, the graduate students are involved as teaching assistants for the undergraduate courses. And so I was very, sort of seeing how psychology was taught. And the differences are very stark, right? Your first year in physics, we did mechanics for the first half of the year. That was the main thing. It was mechanics and math, mechanics and calculus. And then the second half was maybe a little optics. And then it was electricity and magnetism and more math. and that's it, right? That's what you learn. Their first year, you learn a lot of math, and you learn the foundations of mechanics, and you learn the foundations of electricity and magnetism. You don't talk about quantum physics. You don't talk about relativity. You don't talk about thermodynamics. You don't talk about materials. You don't talk about any of that stuff because you're not ready yet. In
so
psychology,
basically like pre-20th century physics.
Yeah, you're doing pre-20th century. You're mostly doing pre-20th century physics. Absolutely. And I think that there's a really good, there's a good argument to be made that this kind of thing is really valuable. That saying we're going to learn tools that are going to help you then any other problem that we're going to be faced with, these kinds of tools are going to be useful. So we're going to focus on particular problems, and a lot of the problems are not just the topics because they're the older topics, but they're also the topics on which a lot of the methods were developed. So the methods that were used to solve problems in mechanics and in electricity and magnetism are very similar to the computational, the mathematical, the methodological tools that were used to study things like thermodynamics or quantum physics or relativity. Contrast that with psychology, whereas you do this kind of broad sweeping survey where you have to learn like the whole history of psychology, and you learn a lot of facts and kind of theoretic ways of thinking about things and metaphors and terminology, and there's very little about how anything works, right?
Yeah, you get experimental. Well, maybe it's probably different between each country, but I did mine in the UK, and yeah, you had like how to do an experiment, basically how to run one,
right?
Stats. That was basically it in terms.
Yeah. So how to run an experiment, but again, where do the hypotheses come from? Right? You just make them up, right?
Yeah.
No, I mean, I did a master's in psychology before I went to do the PhD, and I had to take a research methods course, and yeah, it was just, oh, what's your hypothesis? Just make it up, and then go test it. And I remember when I got really into when I was a grad student, I went off on a number of sort of deep dives onto things that I don't work on anymore, but I was really interested in learning and memory. During my master's degree, I worked in a psychophysics lab working on visual attention, and I became very interested in the mechanics of sort of spatial memory and learning. And I read a lot of papers on these topics. And I read papers written by cognitive psychologists, and I read papers by computer scientists and roboticists, and those papers were better. And what they conveyed was almost always to me anyway, a much richer understanding of what these things were and how they worked, what memory is, how it works, what learning is, how it works. The reason is they had to build tools that used their ideas, and those tools had to work, right?
Yeah.
Whereas if you're a psychologist and you just have to come up with an idea that sounds good to other people, it doesn't do any work.
And you find a directional effect, yeah. Those are the two things.
Yeah, basically. Find a directional effect. Like, oh yeah, if this happens, then this happens more than the other kind. So, I mean, I think I would lose a lot of topical information and say you can always learn the topics.
But isn't there also value to that? Because I'm kind of in two minds about this, because I completely agree with what you said. But I also really value that I was exposed to a lot of different ideas in my psychology, like in terms of like almost finding your topic and then learning how to do research, because I guess most people who do psychology don't necessarily want to do research, right?
Yeah. I do agree with that. So as soon as I finished saying it, your exact objection popped into my head, and so I'm glad you said that. Yeah, and also, I mean, it's very clear the problems in, let's say, physics are much, usually, at least at the undergraduate level, much more clearly defined, right? Like what happens when you throw something up and it comes back down. And we want to know how fast it comes down, right? It's very easy to articulate that problem. Whereas, like, how is a memory encoded? Like, that's a really hard problem. So I'm in a cognitive science department now. And one of the things I really love about the cognitive science approach is that it integrates cognitive psychology with computer science, but also with philosophy. So we take the side that you need to be able to build computational models of these phenomena to really understand how they work and interact with, all the behavioral stuff and the neuroscience stuff. Like, you should be able to model it, but also you should be able to engage with philosophy of mind and consider the question of, what are we talking about? What are these things made of? What is it? Does it make sense to think of these things in this way? What would be an alternative way of thinking about these things? And engage with those questions in a serious way. Because I think that, unlike physics, seems to be exactly your point, is that the parts that we're dealing with, the systems we're dealing with, are much less well defined and are much less intuitive. So yeah, being exposed to ideas, whatever they are, I could stay on memory and talk about things like, visual spatial sketch pads or connectionist models of semantic networks, or, the idea of like David Marr's levels of understanding, right? Kind of computational, algorithmic, and implementational, and how these are different kinds of questions. I think all that stuff is super important. So it's not obvious to me where the lines should be drawn in training and what needs to go and what needs to stay. And I think that, a complementary to that, I think that obviously I think that everyone should learn some modeling. Anyone who's a scientist, who's actually a researcher, should learn some modeling and should learn to engage with the models and understand modeling papers and what models say and don't say. That doesn't mean that everyone should become a modeler.
You should at least be able to understand it and have a rough idea of what they're doing. Yeah.
And I think of this in a way that, like, I think behavioral ecology, my impression is that, like, behavioral ecology as a field is very good at this. Whereas that most behavioral ecologists appreciate, or at least many do, appreciate the value of the models and what the predictions are from the models and how the theories are formalized in models. And they do research that are, driven by the lessons that models have provided, and predictions that models have made. But it doesn't mean everyone's doing modeling. In fact, most people aren't, right? And I think there's a lot of reasons for that, right? Is that we wouldn't learn anything. You actually have to go out and study the world sometimes. And then, also there's just different skill sets and interests. Like, psychology would be a much poorer field if there weren't people who just were obsessed with experimental design or just loved spending hours and hours in the lab. Like, I want those people there. I don't want them working on models. But at the same time, I want people working on models. And I don't think it's an issue in psychology in particular that has to be resolved if the field is going to move forward, is a greater respect for theorists, and to say we are going to support people who focus on theory. I mean, I was once talking to someone in a psychology department, and I said, would you guys be willing to hire a theorist? And they said, well, not someone who only does theory. If they only did modeling and theory, that would be, we can't hire them. They would have to also do experiments. And I was like, well, that's crazy, because you don't demand that your experimentalists also do theory and also do modeling. So it's viewed as this add-on, this sort of thing that's kind of nice to do on the side. But I think of it as so fundamental to actually learning anything in science, that if you're not going to invest in formalization and informal theory, then you're past a certain point wasting your time.
I had a thought when I read that part in whatever paper of yours it was where you mentioned this need for a theorist. I'm not sure I agree with this thought, but I find it kind of interesting. And that's, did we kind of, to some extent, what's the word? Can't think of a proper verb. But did we basically just make those people part of economics? Because I feel like a lot of economists who do theoretical work, the topics sound like psychology papers to me. Some of them, they talk about motivation, self-discipline, and all these kind of things. And I wondered at some point, like, did we just say, okay, if you want to do formal theoretical work, be part of that, part of economics, and then, well, the problem is then obviously people, they don't talk to each other, so you lose the purpose of it. But
yeah, I mean, I think that's a great point. I was talking to somebody recently, who's a journal editor, sort of lamenting that, I think she said something like psychology seems to have outsourced some of the most important things. That's the word.
Thank you. Yes, that's the word I was looking for.
To fields like economics and behavioral ecology. And I think to some extent that's true. And it's also, I mean, I think the whole idea of hard lines between disciplines of people studying humans is crazy. I was just talking to a program officer at some funding agency about whether or not some project would be appropriate for the social psychology office. And they said, well, it's a little bit on the line between what would be sociology and what would be social psychology. And if we're going to fund it, then it has to be more this kind of perspective. You have to focus more on the individuals. And if you focus more on the social structures, then it's sociology. And I'm like, that's crazy, because
that's what makes it interesting.
The interaction is what makes it interesting. It's the interaction between the individual behavior and the social structure that makes it interesting. But if you have one community only focusing on the social structure and one community only focusing on the behavior, the individual behavior, then you miss out on so much. So yeah, I mean, economics, economics has its sort of own special problems.
Yeah.
But one of the things, a problem that they don't have is a respect for formality and modeling. I mean, people have argued that they've taken it too far, although they seem to be kind of dialing it back over the last bit of time, with sort of behavioral economics and the like. But yeah, you have people, and then there are sort of certain fields of mathematical psychology or cognitive science where people are very invested in doing formal models, and a lot of them I've talked to feel like pariahs in psychology, that like their psychologist colleagues don't respect them. They don't seem to get what they do or why it's important. And that's, I mean, I'm not saying all, certainly there's bad theory and bad modeling, like there's bad everything. So certainly some is not, great and should be revered or respected just by virtue of the fact that they can build a model. But,
yeah.
But that I think it's an important tool. And
yeah, I find it really difficult. Like, I remember when I was in the point I wanted to make is that it almost feels to me that part of maybe the problem is that, at least in the UK, the way it was taught is that you have like one psychology bachelor for everyone who wants to do psychology, most of whom are people want to do clinical stuff. And I just remember in one of the first year cognitive psychology lectures, they talked about the connectionist model, and just half of the people just almost panicked at at like just seeing something that's vaguely mathematical and logical. And I mean, like and because they had like no interest in doing anything mathematical or doing anything that wasn't clinical almost, right? So I almost feel like it might be useful to separate maybe cognitive science, like as a thing in general, from people who want to do clinical, but then, yeah.
Yeah, I think that's probably right, is that clinical psychology should probably be completely separated. I mean, there's certainly certain information. There are probably certain classes that it would benefit everyone to take on both sides. But in terms of I did my master's degree in a program that was mostly clinical, people who wanted to become clinical psychology and psychologists. And
how was that as a physicist?
It was extremely frustrating. I think it probably, helped develop my sort of curmudgeonly attitude toward a lot of psychology. But, it was very, I remember I would just, in a social psychology class, be constantly raising my hand and just be like, but wait a second. Like, why would it be that way? It doesn't seem like there's any good reason to think that. And the professor would be like, well, it's a theory that's developed by, it's based on the writings of this existentialist philosopher from the 1960s. And I'm like, well, how is that a basis for anything? But, and then, so I was talking to somebody else in the class later, and they're like, yeah, we notice you ask a lot of questions. Yeah. And I, with the implication that it was too many questions. And they were like, we just want to get through this and learn write down the things we need to know to get our degree and move on.
Yeah. Yeah. So actually, one other question I had about the paper, models are stupid and we need more of them. I mean, I think, in large part you chose that, title and the way of explaining like why it's good to have stupid models that not oversimplify, but that strongly simplifies things, to just show like this isn't a bad thing necessarily, right? This common criticism. But I was wondering, like, when I read that, like, when kind of is something oversimplified? Like, how do you know you've oversimplified a model, or when kind of does the, in quotes, stupidity of the model actually become a problem?
Yeah, that's a fair question. I think it becomes a problem when you try to make quantitative predictions too soon. There's often a rush to validate everything by prediction, and I think that is sort of the ultimate goal, is to be able to say, well, the model predicts that this should happen, and so we need to go test it. But But we're also dealing with systems that are both so inexact, as I've said, and also so complicated that it may take some time to develop theory that is good enough to make predictions. And I think, one of the things that's still at present very undervalued in psychology, at least, is the idea of doing modeling for the sake of understanding a model system and understanding the consequences and implications of certain assumptions. That doesn't necessarily mean that those assumptions are precise enough to then go out and test the theory in the world. It may be that we need to then, keep pushing through on the theory to get to the point where we can start adding enough complexity or enough precision that it then becomes a reasonable representation of what's going on in the world.
So what is the kind of, when you say you try and create a formal model, what exactly is the goal then?
I mean, the goal, I think there's a lot of goals. There's not just one goal, but, one goal is to say, well, what kinds of structures emerge under certain kinds of constraints that are similar to the kinds of constraints that exist in the world? So I'll give you an example. One of the first modeling projects I worked on in psychology, or as a social scientist, was on some of the human mate choice literature. It's kind of a wacky literature, and I don't work on it anymore. But it was people had been using these models to say, well, how do people make decisions about who they're going to end up with, as a romantic partner, and what criteria do they use? And there was this work done in the 1980s where people said, well, there seems to be this paradox because there's this high correlation between the physical attractiveness of couples. That would indicate to us, the psychologists, that people are searching or, sort of have a good sense of their own attractiveness and are looking for a match. However, if you ask people who they prefer and who they would like to be with, everyone prefers to be with the most attractive person they could possibly get. So how do these things work together? Well, they built a simple computational model where individuals have some attractiveness level that is, everyone else can see and they know about themselves. And they put in preferences either for the most possible attractive partner or the most similar possible partner. And what they found was if everyone's looking for similarity, you get these extremely high correlations, much higher than the correlations you find in the real world. But if you put in preferences for everyone wants the most attractive, you get correlations that are very similar to what you see in the real world. And they said, well, look at that. And the reason is that all the attractive people reject, less attractive people and wait until they get paired with someone who's more attractive. And then to make the model work, they had baked into this thing which they called the prettier at closing time rule, which is that the longer you wait, the lower your standards get. And
okay.
And so then then the next level attractiveness people pair off, leaving only the next, and et cetera, et cetera, et cetera. Well, this makes so that's fine, and that's a nice use of models, but it also makes all these like secondary predictions that are completely ignored. One is that under this, if the assumption of this model are correct, then less attractive people should get married much later. Like that there should be a very strong correlation between age at marriage and physical attractiveness, right? Which is not actually borne out. It also it turns out that there's a number of assumptions, like exactly the strength of this prettier closing time rule, or exactly the strength of preferences. Like you can keep the order of preferences exactly the same, but change the strength of how much a little bit more attractiveness gets you. And it turns out you can make either rule by doing this fit the data as perfectly as you like. And then there's all these other data like like I said, like age of marriage, et cetera, that are completely ignored there. Neither of these rules generate anything looking like realistic curves. You can change the model to make it so that they're more realistic. But then it turns out if you change the network structure, so the models assume that people meet each other and meet potential mates completely at random. But that's not the case, right? There are network effects, right? You meet people who are in your social networks who are doing the same things you are, or going to the same places you are. If you start, messing around with that, you can also get either decision rule to fit the data as much as you like. So the point here is that, the model is useful because it helps you understand how different kinds of decision rules at the individual level can lead to different kinds of patterns at the population level. That's useful to know, and it makes the model valuable. But if you start using the model to then make predictions about what should happen, or to use data in the world as a way of validating one particular version of the model versus another, because there's a better fit to the data, well, there are a bunch of assumptions in the model that don't fit what's going on in the real world. And when you start messing around with those assumptions, they completely change the fit to the data. So you need to know information, not just about what the individuals are doing, but let's say what the strength of their preferences are, and also what the structure of their social interactions are, before you can start saying anything about how good a fit to the data it is. And that's what I mean. Like, the model is too stupid to fit to the data because it doesn't, it hasn't become specified well enough yet. It doesn't mean it can't get there, but it means that, it's not ready yet. And you need, and this is also, like, just to make the same point I made earlier, this is why you need people who are dedicated theorists who can spend time working with models and understanding how models work and when a model is or isn't ready. And you need someone who's not just tacking on a model to their experiment as a way of sort of, trying to strengthen their argument without really understanding how these kinds of models work. Right. What a modeler does not do is prove your theory with math. Right. The model is itself information that should change your theory or add to the theory.
That was kind of what I was thinking of doing. I feel slightly caught out right now. Not as explicitly, but that was kind of.
I think it's a really common assumption.
But then it's the kind of iterative process of seeing under which assumptions what works, and then
I've sort of just decided, somewhat arbitrarily, but it's because I like it, that I was going to become an expert in this kind of modeling and modeling social behavior. It's just I just really love it, and so I'm really good at it, and I know a lot about it. I'm not perfect at it. I've made models published modeling papers, and I'm like, I probably could have done things differently. But I know a lot about it. And part of knowing that much about it, it highlights how much there is to know. There's so much to know. And that's, it's like any expert, any researcher, any professional, right? You want to become top in your field. You want to know all the things that you need to know to do your job well. And in order to be, it takes a lot to be a very good modeler. And I'm not saying, like, I certainly don't think I'm the best modeler, and I think there are a lot of great modelers out there. But a lot of the best modelers are ones that, they have invested a lot in learning about models. And they're probably not the best experimenters, right? I'm collaborating with experimenters now, and I realize how much I don't know about experimental design and analysis. It's hard. It's really hard. And, like, hats off to the people who do that. Right? The point is, like, division of labor. The point is that I can do what I do because there are people who do what you do, right? Who dedicate their lives to become really good experimenters or good field researchers or good data scientists or whatever. And, science, I think, works best in teams where there are people who can build on each other, and models and theory can inform experiments, inform data collection or analysis. Because we're all trying to figure out, not just, we're all trying to figure out, like, what the best questions to ask and the best ways to get them answered are, that's going to, like, increase our understanding of the world in the most meaningful way.
Well, thank you for sharing your expertise in these papers, because for people like me who haven't known, they're very useful.
Well, it was a pleasure.